Good afternoon, everyone. And I'm Shunji from Chiba University. And I'm very happy to share our research progress over the past 1 year. And also, I'd like to thank my project members for your hard work over the past 1 year. Okay, let's get started. So as you have been seeing, so currently the 4 projects are running for the Moonshot Goal rate. And so we started our project a little bit later than the other project. But what we are aiming at is to mitigate the rain-induced disaster for stationary heavy rain. And we started our project last December. And what I'm going to show is our research project progress over the past 10 months. Okay, and so first of all, I would like to share our research and development strategy. And so in Japan, so we have been suffering from the heavy rain-induced disasters. And for such disasters, the water vapor coming from the ocean played important roles. And here I'm showing the 2 examples. And so both cases, the water vapor is coming from the ocean massively and occasionally, so that they introduce the catastrophic damage in Japan. And if you see the world, so we see the similar disasters. And there may be several possibilities to mitigate such disasters. So one may think to limit the evaporation from the ocean, and one may think to change the large-scale circulations. But in our opinions, it's very difficult to achieve that. And our strategy is to reduce water vapor before arriving over land. So the heavy rainfall would cause disasters if it happens over land. But if we could generate heavy rain artificially over upstream oceans, so we could reduce the damages. And so for realize the generation of heavy rains, so we think there may be 2 steps. So one is to generate convections over ocean. And in other words, so we need to lift up the atmosphere dynamically beyond the level of free convection, or heating the atmosphere thermodynamically. And for that purpose, we are thinking to use several interventions, such as kite or floatings, or like heating up the atmosphere by microwave or gas. And so maybe we could generate a convection, but we should generate the heavy rain. And the second point is to organize such convections. And in other words, so we need to lead back-breeding type successive rains using cold pool. And if we could succeed to do that, so we could reduce water vapor reaching to land and leading to the reduced rain. And this is our strategy. And so we made a rough estimate of level of free convection and sink, and to think about how much energy or intervention we need to generate. And fortunately or unfortunately, what we are targeting is conditionally unstable atmosphere, having the massive water vapor in the low troposphere. And so once we could, so therefore, the level of free convection or sink energy is very low compared to the stable atmosphere. So that's why, so we are thinking there may be a chance to generate convection by artificial interventions. Okay, for weather control, so we need to think about several aspects. So, but the most important aspect is the meteorology, to think about how to generate heavy rains. And our first question is whether or not we could generate or mitigate heavy rains by artificial interventions. And of course, so we need to do the numerical experiment prior to the field experiment. And at this moment, so what we have been thinking about is the kites or overseeding. And we have been exploring how such intervention changes the atmosphere. And I'm going to show some preliminary results using the numerical weather prediction model. Okay. And the first intervention is the so-called overseeding using Wolf model. And what we explored is the heavy rain in Hiroshima in 2014, and that have more than 240 millimeter in 3 hours, and that caused landslides in these regions. And in this event, so as you can see, this so I'm going to show an animation without and with intervention. And in this event, so we had several deep convections, and that caused the heavy rains in this region. And so we did the overseeding to generate the cloud ice over the over high troposphere. And this overseeding aims at 2 points. So one is that to remove the water vapor by the overseeding, and the second purpose is to stabilize the atmosphere a little bit more because of the latent heat. And we did overseeding by the aircraft, and so this is a numerical experiment. And by the overseeding, so we see the increase in cloud ice in the higher troposphere. And if we see the changes in the precipitation over 3 hours, so we see the reduction in the intensively precipitated region, shown by the black lines. And we also estimated economical damage reduction for these cases. And so we see the approximately 0.5% damage reduction. That corresponds to the 200 million Japanese yen. And so this preliminary experiment shows that maybe there may be a, economical, benefits to mitigate heavy rain by our interventions. Okay, and another experiment is a kite over ocean. And so this kite aims at lifting at atmosphere and to cause rain. And so here I'm going to show the 2 experiments. So one is for the heavy rain in Kyushu, and we set the 21 kites over upstream ocean. And if you see the precipitation with and without and with control, so you see the reduction of heavy rain in the targeting region. But we also see the increased precipitation in the upstream ocean. So it means if we could increase the precipitation over upstream ocean, so we have more chance to reduce precipitation in downstream region. And this is an example. And another example is precipitation associated by a typhoon in 2015. And this is known to be a Kinugawa heavy rain in Japan. And we also consider addition of the interventions with 100 kites. And again, so without and with control, so we see the increase in precipitation in upstream region and followed by reduced precipitation. So at this moment, we are thinking 2 interventions, and such 2 interventions may change the atmosphere. But from our preliminary experiment, we also noticed that sometimes intervention worked, but sometimes intervention didn't work. And it means intervention, maybe in the atmosphere, there may be a critical point or timing when the intervention worked well. And it means, so we also need to think about the mathematical problem, how to optimize the manipulations. And myself is a researcher of ensemble data assimilation, and I tend to see this problem as an inverse problem. And it means, so we need to optimize the intervention to have largest impact. And for that purpose, so we are also working in mathematical and data assimilation research. And I'm going to show about the objective of mathematical and AI researches. So suppose, so there is a trajectory leading to catastrophic disaster. And but we would like to add control inputs to change the atmosphere toward desirable regime. And for that purpose, so with mathematical control methods are necessary to optimize interventions. And for the first steps, so we started introducing the model predict control into the data assimilation to optimize the intervention. And so I'm going to show a schematic image of our methodological research. So we know the atmosphere is have uncertainty, and therefore, so we have been doing the ensemble forecast based on the analysis of ensemble. And this is an example of ensemble forecast for a heavy rain case. And if you see the precipitation, so your eyes may think that these precipitation patterns are dissimilar, but the important point is that each of them could come to, because in the atmosphere there may be such trajectory toward each of them. And what we would like to do is to find a desirable trajectory reaching to the desirable future, and to synchronize the real atmosphere to be such a simulated state, and with limited interventions. This is what we would like to do. And for that purpose, we think that we need several steps. So first step is to boost ensemble forecast. So our ensemble forecast can be limited by the computational resources, but if we could boost the size of ensemble, we have more chance to find the best trajectory. And the second step is to find a desirable trajectory from the ensemble forecast. So we need to select the best scenario or possible scenario that can come true and that we would like to fulfill. And the last step is to optimize the interventions with model predictive control. And for the first step, so we plan to boost ensemble using the AI-based weather predictions. And we have some preliminary outcomes for the 3 steps. And the first one is AI-based weather prediction. And as you may know, currently, the AI technology is advancing rapidly, and there is no reason not to use such techniques. And at this moment, what we are developing the 2 AIs. One is for medium-range ensemble forecast. And so far, so we succeeded in coupling the AI-based weather prediction model with the LETKF, which is under the ensemble Kramer filter. And also, so we assimilated real observations and succeeded in the running data assimilation cycle over 1 year. And so it means the first research succeeded in coupling the AI model and ensemble Kramer filter. And so because of the AI model, so we can increase the ensemble size easily. And but predicting the heavy rainfall by AI is known to be difficult. So therefore, so we are also training an additional AI to have intense precipitation. So this additional AI trying to downscale the precipitation and also try to boost the ensemble using the diffusive model. And at this moment, what we are using is the so-called swing unit and for with addition of the diffusion model to achieve the 6-hour forecast. And again, so predicting the intense precipitation is difficult, but so far, so we succeeded in reproducing some intense precipitation. And here, so this is we see the heavy rainfall as observed by the radar observation. Okay, so we are trying to boost size of ensemble using AI. And the second research is to find a preferable trajectory. And in state space, so again, so I'm showing the precipitation predicted by the ensemble forecast. And again, so for our eyes, such precipitating members are dissimilar each other. It means that maybe in state space, we can't differentiate them. But in our mathematical hypothesis is that in the latent space, so we can illustrate a kind of landscape, how they came to. So in the latent space, so there is an initial condition, and so maybe some members reaching to the heavy rain trajectory, but some members reach the non-disaster trajectory. And we need to differentiate such trajectories. And the atmosphere itself is known to be chaotic. And we know the chaos system should have some attractor or trajectory. And what we are trying to do is that to find such trajectory for heavy rain case. But for the first trial, we applied mathematical landscape analysis for typhoon case because we can see the trajectory easily by the typhoon track. And we applied the landscape analysis for typhoon dolphin case 2020 for the ensemble prediction data. And this landscape analysis employs clustering and developing the directed graph followed by a graph Fauci decomposition to provide the potential or the possible trajectory. And here I'm showing the 2 examples. So the left one is the Hodge potential corresponding to the landscape, and the right one is the trajectory analysis showing the possible trajectory. And this kind of mathematical research can help us to find the, the separation of scenario or to find the possible trajectory. And this is a second research we have been doing. And the last one is the optimization of interventions. So again, so for weather prediction, so we haven't think about the interventions. But in the case of weather prediction, so we need to optimize the interventions to realize the preferable future. So it's a kind of optimization or inverse problem to find the best position or best intensity or best timing of interventions. And in the nonlinear control field, so the model predictive control is widely used. And we started coupling such model predictive control with weather prediction model. And what we did is a so-called convex optimization using the numerical prediction model. And what we applied is for our warm bubble experiments. The problem is to optimize the perturbation of potential temperature for leading the preferable precipitation. Yeah, and so in the left side there is the equation. It means so we would like to minimize like initial perturbations with satisfying the cost function. Okay, and right side, so I'm showing the two results. So one is the L2 norm, and the second one is L1 norm. And the bottom figure shows like changes in precipitation. And black line shows the precipitation in control. It means without intervention. And what we would like to realize is to reduce the intense precipitation. And so we set like our cost function is to reduce the intense precipitation less than 90%. And we optimize like initial interventions. And so L2 norm provides like the barriers and spatially smoothed interventions, but the L1 norm provides like a point-wise interventions. And we are thinking that the L1 norm would be more suitable for atmospheric control because our control may be point-wise, and maybe so. And we would like to optimize such point-wise interventions. And but what we demonstrated was such mathematically explored model predictive control is working for weather prediction model too. And we are planning to extend this experiment for realistic like heavy rain cases. Okay, I'm going to summarize my presentation. Okay, as I mentioned, there are several problems or aspects to be solved toward weather control. And at this moment, we concentrate on the meteorological and mathematical researches to think about the way to generate heavy rains or how to optimize manipulations. But we also noticed that there are social issues that should be solved by like 2050. And we are also working for the RRI, which is responsible and research innovation research to realize in society or to have a social agreement. And also, we are working with like legal researchers to how to design the society or how to design the laws. And also, we are working for manipulations, how to realize such interventions as I mentioned. And I'm showing a roadmap toward 2050. And at this moment, so we are doing the so-called like weather prediction-based simulations. And at this moment, we have been working for the numerical experiment with numerical weather prediction models. But so we have some preliminary results that showed like a cloud seeding or kites may be useful for interventions. And we plan to start developing such interventions and followed by a small-scale field experiment or a large-scale field experiment by 2050. But so this is a scientific research and development. And we also need to think about the LC or RRI issues. And at this moment, we are working to identify social issues. So what is the possible problems, or what is the potential, how to say, risk, or what is the concerns by the citizens. And we are trying to identify what kind of problems should be solved for LC and RRI aspects. And we plan to extend this research for cost estimate or to work for the social agreements. And also we need to develop social systems such as designing laws or insurances. So this is like a plan so far. Okay, let me summarize my presentation. So we started a new core project since last December, and we are working for heavy rains. And at this moment, we have a preliminary good result for heavy rain cases for three like experiments. And we noticed that our projects need to be enhanced for engineering study for realizing the interventions. And also, we are thinking that international collaboration is very important for impact and risk assessments. And we are always happy to take any suggestions if you have. Okay, that's all I have to present today. Thank you very much.